The third kind of electrolysis is building on one of the concepts what I discussed in this thermodynamic chapter. And this is that actually when we're using steam instead of liquid water, we can operate the cell at lower potentials. So this kind of high temperature electrolysis of steam, or HTES, we can operate this cell at lower than 1 volt. And this is usually around half a volt lower than for the AEL and PEMEL process. Another advantage of this kind of cell is that it can actually act as a fuel cell and an electrolyzer. So it can basically convert chemical energy into electrical energy, as well as electrical energy into chemical energy. And this is particularly suitable for locations with fluctuating supply and demand, where this cell, depending on if you have high demand or high supply, can just be adjusted to a different mode of operation. So the analogous cell here would be the solid oxide fuel cell. However, this kind of cell requires additional infrastructure usually and is a little bit harder to maintain, so this is a concept which is currently mostly under development. The operating principle of such cell is also the electrochemical splitting of water, but of a different aggregate state. So here we electrochemically split steam instead of liquid water. This, of course, requires way higher temperatures, and this is the reason why this kind of cell is typically operated at temperatures of 850 up to 1000 degrees C. So the energy required for the vaporization doesn't have to be supplied by our electrical energy as it is for our liquid system. So this kind of heat part, which our electrical energy has to be used for as well, is falling away basically. And this allows us to save around 16% electrical energy in this kind of process. The cathode in this kind of system is supplied with superheated water and therefore produces hydrogen. And our membrane is a conducting solid electrolyte. So it's basically a solid which is able to conduct oxide ions, O2-. How does this look in practice? So again, we have a different kind of reactions basically, because we're using steam here. On our anode, we still facilitate the oxygen evolution reaction. We are reacting oxide ions and form 1/2 oxygen and 2 electrons. And on our cathode, we have the reducing reaction, the hydrogen evolution reaction, where we are reacting water and 2 electrons to form hydrogen and oxide ions. The overall reaction is the same as for our alkaline and for our acidic electrolysis. And again, you can apply the same concept by looking at what is our charge carrier, and the only charged species here is our oxide ions. So now our oxide ions are the charge carrier. The cell now looks the following. We do have a cathode here on the left side and an anode on the right side. Now on our anode, we have a reaction of oxide ions to oxygen and electrons. Now where does this oxide come from? Well, this actually comes from the cathode side. On the cathode side, we're supplying this steam, this superheated water, and we are reacting our water with electrons to form hydrogen. This can again be extracted directly at the cathode, and we're forming oxide ions. These oxide ions will now be taken up by this membrane, or in this case, it's better to speak of a solid electrolyte. And this oxide ion traverses to the other side, where it's then basically oxidized to oxygen and electrons. And the oxygen can then escape through the top on the anodic side.